tremendously important to mathematics, okay? First of all, that looks eerily similar to the questions that we were doing in Chapter 7, does it not? Okay? And then this is the first thing I want to talk about, because in Chapter 7, we had a statement in those corollaries about geometric means that said, in a right triangle, if the altitude to hypotenuse is drawn, okay, then you get geometric means, correct? About segments, legs, all that kind of stuff. And here's my question. In order for the geometric mean stuff to be valid here, to work here, we first, because of the law of detachment that we learned in Chapter 2, we have to have in front of us a situation that models that statement that I have written up there, because that's the if part of that corollary. If in a right triangle, the altitude is drawn to the hypotenuse, okay, then legs are geometric means, okay? Is that occurring in this problem for us? Do we have a right triangle in which the altitude is being drawn to the hypotenuse? So the question is this green triangle, is it a right triangle? I see some heads shaking no. The correct answer is no. Because and I'm going to say we're actually able to verify eventually that it is absolutely not a right triangle. But before we do that, let's actually say we don't know, okay? I cannot confirm that it's a right triangle. It could be, but I can't confirm it. Does that make sense? So because I can't confirm it, this geometric mean stuff that we talked about in Chapter 7 cannot be used, okay? And the reason I don't know it's a right triangle is for this mere fact that they don't put that symbol there in that corner, right? Okay? If this was a right triangle, my hopes are that you would argue that that would be the most likely situation where that angle is the right angle, okay? So I don't know this thing to be a right triangle, so I'm not going to try to use geometric means. I put that on a quiz coming up. I put it on a test that's coming up because I want to make sure that we understand that part of mathematics, okay? And it's all across mathematics. You cannot use a rule, excuse me, puberty. You cannot use a rule or a property or something of that nature if what you are working with does not match the hypothesis of that rule, property, or whatever. That kind of make sense? Okay. However, we do have the ability to look at this in separate right triangles. Is that a right triangle? And then that green one is a right triangle as well, correct? Okay. And we're going to see a lot of this as we move on throughout the rest of the course, that if my goal is to start or to find X, usually I'm not going to be able to directly find X. I've got to start somewhere else. And if I want to decide where to start, I usually start in the triangle that I know the most about. I know the most about the blue one, right? You know two sides of the blue one. You only know one side of the green one. So I'll start with the blue one and see if I've got any ideas here. So I'm going to call this distance here just B. Okay? So let's say B squared plus 2 squared should equal 2 radical 5 squared. I had a lot of people in the last class, they said I knew the exact approach to doing this, but for some reason, just the way the answer was working out, they said I was usually about half off in regards to my final answer. Okay, and it's because of how we have to square that number right there, 2 radical 5. Let's go through and just kind of simplify this. Left hand side is B squared plus 4, and now this right hand side, and this is where This is where we have to remember our Algebra 1 skills. Okay, this is Chapter 7 of Algebra 1, maybe a little bit Chapter 9 of Algebra 1. And that's what stinks about high school math, high school science, especially the sciences that actually allow you to start like recognizing real-life phenomena with mathematics, like physics and chemistry and that type of thing, is that it relies on your mastery of algebra. Okay, and if you're not good at algebra, then you're not going to be able to display that you're good at chemistry, that you're good at geometry, that you're good at trigonometry, physics, that kind of stuff. Does that make sense? And I think I've hopefully belabored that point to you the whole year so far. But here comes some algebra then that we have to remind ourselves of. Okay? And what I'm going to do is just kind of think about this. If I look at 2 radical 5, 2 radical 5, that's 2 times radical 5. Okay? So 2 is a rational number. Radical 5 is an irrational number. Okay? With our algebra, we usually don't multiply those together. The only way that I could multiply those together is to actually do it with a calculator, get a decimal, and then round that decimal. Does that make sense? And the moment that I round that decimal, I really don't have 2 radical 5 anymore. I got something either bigger or smaller than 2 radical 5, depending on how I round it, right? Does that make sense? Okay? So, we don't want to do that. Okay? What we're going to do here is realize that that's a product of 2 numbers. If it's a product of 2 numbers, it's something like this, like A times B raised to the 2nd power. Okay, and if you remember how you did that last year, okay, that means you have AB being multiplied by itself 2 times, right? Does that make sense? If I did that, can I rewrite that as A times B times B? And is that A squared times B squared? That make sense, everyone? So I started with this, and it turned into that. Okay? Now I'm going to make it a little bit, I'm going to go one step further with a different example here. What if I had like A cubed B squared, and I wanted to raise that to, let's say, the 4th? Then that would be A cubed B squared, right? How many times? This says how many times I want to have A cubed B squared? 4 times, right? So let's see if we can just paste that in there quickly 4 times. All right, so we get that 4 times. But A cubed, doesn't A cubed mean A times A times A? That makes sense? Okay. How many times do you have that written in here? A cubed shows up 4 times, right? So let's see. So we got that. 2 times, 3 times, 4 times, right? And then B squared would be B times B, right? But don't you have that B squared showing up 4 times? So I'll have, there's another time, and there's my 4th time. How many A's do you have here total if I count those up? 12. And repetitive multiplication, I write using exponents, A to the 12th. This would be B to the 8th. This is what I started with. This is what we got to. Do you remember taking that 4 and multiplying by that 3 to get my 12? And multiply that 4 by that 2 to get that 8? That make sense? And that idea, so that algebra, the reason we do it this way, we come up with these rules, is because what if I had like A to the 35th, B to the 74th, and I want to raise that to the 5,000th power? You don't want to write all those out like we just did, right? It was a pain in the butt writing out 12 A's and 8 B's, okay? So we find these patterns and we recognize that, okay, if we've got a power to a power here, we can just multiply each of the powers by that 2nd power, okay, the outermost power. So when I take this 2, doesn't 2 have an exponent of 1? It's just understood. And we can do this radical 5 2 different ways. You want to write it as radical 5 this way. with a power of 1 like that and square it. And now do a power to a power. So I'm going to take that 2 and multiply it by that 1. So it gives me 2 squared. And let's take that 2 and multiply it by that 1. So it gives me radical 5. I'll write this way, squared that way. So what's 2 squared the same as? 4. What's radical 5 squared? What do radicals and powers of 2 do to one another? Cancel each other out. They're opposite, or they're inverses. So you need 4 times 5, which is 20. Okay? So 2 radical 5 squared is 20. Now, I told you we could do it a different way with this radical. I think I mentioned this last week. A radical can be rewritten as an exponent that is a fraction. And if it's a square root, I write it as to the 1/2 power. That's the one we're going to use the most. That's the only one we'll talk about here for a moment. So radical 5 and 5 to the 1/2 are the exact same thing, just different symbols for the same numbers. Is that okay? Well, now if I raise it to the second power, 2 to the first raised to the second, that becomes 2 squared. And now if I multiply those two things, does it just give me 5? And again, I got 4 times 5, which gives me my 20. Okay? If you're to type this on your calculator, here's where a lot of people in the last class were expressing where they got things wrong. Type it in my calculator. Let's say I go to one of your handheld calculators like this. And we go 2 radical 5. And then we square it. Okay? If I do that, understanding my order of operations, parentheses, exponents, multiply, divide, add, subtract, and how the exponent rule says that the exponent only gets applied to the thing that it is directly behind, correct? You guys agree that that 2 is only behind this radical 5? Directly behind the radical. It's not directly behind the 2, right? So if I do this, we said we should get 20, but it gives me 10. Because what's happening is that you're squaring this radical 5, but you're not squaring the 2. If I were to do this correctly, I need to have a set of parentheses on my calculator, like this, and now square it that way, and there you can see that you get your 20. Does that make sense? Okay. We always make the argument, well, I don't like using my calculator. I don't like students sometimes using their calculator because we're not certain how they work. And that's the argument we make, but it's not that we don't know how they work. We absolutely 100% know they work. They work by abiding by and only by abiding by, that sounded weird, the order of operations. So when we don't know how our calculator is working, we really don't have a good grasp of what our order of operations are. Okay, so that's why I want to make sure that we understand when we're doing these types of problems. So now I can subtract 4 from both sides. I get b squared is equal to 16. So what's b got to be then? Got to be 4, right? Square root of 16 is 4. So now we've learned something about the green triangle here. We now know that this distance is 4. So can you start this whole problem over with just that green right triangle? So we'll have 4 squared plus 14 squared is equal to x squared. We get, it's 196, not 169. 196 equals x squared. That gives me 212. And then x will be root 212. Okay? Just thinking about some things that divide 212. What number do you know will divide 212? Even, right? So 2 is kind of your go-to when it's even. It gives you 106. 106 is even. Gives me 53. 53 is a prime number. So that if I want to break this radical 212 down, this is it. It's basically that right there that I just circled is showing me that radical 4, or 4 itself, is the largest perfect square that divides 212. So this would look like maybe radical 4 times radical 53, but we can change that radical 4 to 2. And that's the answer that we're looking for. Okay? Now, I think it makes sense to see why or if we know that the triangle cannot be solved using what we did in chapter 7. So let me trying to find a towel to wipe the board off. Stealing my towels. All right. If this overall triangle here was a right triangle, and we had this dotted line being our geometric mean, okay, or our altitude drawn from the right angle to the hypotenuse, wouldn't we be able to say that this would be a leg of the right triangle? That'd be a leg of the right triangle. So legs were geometric means as well. So I can put x and x there. But it's the geometric mean between, this would be the whole hypotenuse. If that's a right angle up there, that bottom 16 would be our whole hypotenuse. And then the 14 would be the portion that is touching that leg x, correct? Okay, so this is chapter 7 stuff. If I cross multiply, I get x squared is equal to 16 times 14. Square root both sides. Square root of 16 is 4, right? Square root of 14, just square root of 14. So that number right there, if this thing was a right triangle, this distance x should be 4 radical 14. We just found x to be 2 radical 53, right? Are those two numbers different? And we know the 2 radical 53 is the correct answer because I used a theorem that we knew was valid because we had right triangles and we knew we could use the Pythagorean theorem. Okay? So what I'm trying to get at here is that people, like I said, people try to initially do this using section 7.4 information. But we don't know that to be a right triangle. Now that we've done this process and found x using appropriate, valid theorems that work for this image, and we know x is 2 radical 53, if I use geometric means, I get x to be 4 radical 14. Those two numbers are different, so I know this is not a right triangle. Okay, so I can make that, at the beginning we said we weren't certain. We were uncertain of whether that was a right angle there. Now doing this, I know for certain that's not a right angle. Does that kind of make sense? Okay, so that's kind of using multiple ideas with one another to validate one or the other. Okay. Towards the end of that assignment, I was giving you questions, and you're going to see today maybe the purpose of those questions. But I was giving you stuff like, 4 over root 13. And I asked you to rationalize that. You guys remember how to do that we kind of spent a little bit of time last week talking about this. You guys remember if there's a radical in the bottom, we don't like that? So what do I need to multiply that by to get rid of it? Anybody? I'm going to multiply by a radical 13. I'm going to multiply. So what has to happen, if I gave you a number, let's just say I give you the number 13. What do you need to multiply 13 by to generate a perfect square? 13, right? The only thing you can do, if I give you a number, the only way through multiplication that you can turn that number into a perfect square is to multiply it by itself. So what I want to do is I want to take that 13 that's in that radical, that's called the radicand, R-A-D-I-C-A-N-D. I want to turn that 13 into a perfect square. So to do that, I multiply it by itself. And in my radical then, I get 169. Okay? Now here's the thing. If I leave the numerator alone and just carry the 4 over to my final answer, I've actually changed the size of the denominator, so I've changed the size of that number. Does that make sense? I don't want to change the size of the denominator. Okay? So if I multiply the top by radical 13, okay, I have now proportionally changed the denominator and the numerator, so it's really the same number. Does that make sense? Same number that I started with. But 4 times radical 13 is 4 radical 13, right? Now here's the thing, and this is why we call this rationalizing the denominator. What's radical 169? It's 13, right? And now we started with a radical, which is an irrational number, in my denominator. And in my final answer, I get a denominator that's a rational number, 13. Okay? That's going to be asked of you. Okay? We're going to ask a lot of homework questions, a lot of test and quiz questions. If you type this answer in, you're going to be wrong. Okay? We're going to want that one there. Eventually, you start to get the hang of it if I go like to radical 7. Okay? What you're going to find out is that essentially that denominator goes up to the numerator, and then you're left with just the radicand on the bottom. Does that make sense? There's a pattern to that. But with patterns, I want to make sure we understand where the pattern comes from. It's this idea of multiplying by radical 13. Okay? We'll build on this. Eventually, we'll talk about cube roots and fourth roots and that kind of stuff and how we do that process for when we get to volume and areas. If we have something like this, let's go 2 over let's see here. Let's go 12 over radical 3. We'll multiply by radical 3 over radical 3, right? Gives me 12 radical 3 up top. I'll multiply straight across. What's going to give me on the bottom? 3. Okay. Now, here there's some reduction that can be done here. Okay. Remember what we're doing here. We're multiplying 2 numbers. 12 is a number. Radical 3 is a number. Can I rewrite this as 12 over 3 times radical 3 over 1? Is that fair to do? If I multiply those straight across the top, do I still get 12 radical 3? If I multiply straight across the bottom, do I still get 3? Does that make sense, everyone? So this is okay to do. We can rewrite this way. And the reason I would want to do this is what does that turn out to be right there? 4, right? So you get 4 times radical 3 over 1, which is just going to be 4 radical 3. So when we get something like this, you are allowed to reduce those numbers if they obviously divide each other. Okay? What a lot of people want to end up doing is changing this to 4 radical 1 because they want to divide the 12 by 3 and they want to divide that radical 3, that radicand of 3, also by 3. And you can't do that. Does that make sense? And the logic of why you can't do that is this here. All right. Let's do this real quick. So like a lot of this stuff, guys, like the algebra here that we're talking about, like I had, like you guys all hear the phrase hindsight's 20/20, right? Okay, if I could look back on, what I know now to, how I maybe operated in other situations in the past, I would know that I could operate in a different manner, right? I know what you guys are coming across. I know the math that you're going to need. You've heard me say this over and over again. But when I go over that kind of stuff, the reason I'm doing that is because I currently still have students that are in my senior level and junior level classes making those types of errors and mistakes on things that we use every single day in every single problem. Okay? So I want to make sure that you guys clean those things up or have the opportunity to clean those things up before you get to a point where it is, every problem, every step involving those types of numbers and that type of math, to where you don't get bogged down and frustrated and overwhelmed with it at that stage. Does that make sense? Okay, so I think that's very important for us to kind of come to terms with. I'm going to, so I got some notes here, but I don't really want to go over the notes the way I've got them set up. So let's do this. Let's go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I'm going to create a right triangle here. And the way that I created that right triangle was to guarantee that this side was 6, that side was 6, and that's a right angle. Okay? Give me some names for that triangle real quick. Give me a way that you would classify that or identify it based on the features that I just gave you. Say again? It's a right triangle. And it's isosceles. So we call this a right isosceles triangle. Okay? Furthermore, you should know a little bit about that angle there compared to that angle there. We know about those two angles. They're the same. Base angles of an isosceles triangle, or the acute angles of a, I won't say acute angles, the base angles of an isosceles triangle are congruent, right? Okay? And if that isosceles triangle is a right triangle, then they are, they're both acute as well. Okay. If those are the same, they have to add up to what number? All three of them have to add up to 180, right? And you've already used 90, so they both have to be 45 degrees. Okay? So, a right isosceles triangle, a lot of times, is referred to as a 45, 45, 90 triangle. Okay? But what I want you guys to know is that vocabulary is referring to the same thing and the same practice that we're going to do here in a moment. Question on the end of course exam could talk in the directions about a 45, 45, 90. And if they do, I think that's probably beneficial for us. But at the same time, they could say in the directions, right isosceles triangle, which would convey the exact same information to us. Okay? So I think we need to link those two things and know that those two things are the same. Those are equal. Okay. Do me a favor real quick. Solve for C. Just on your own. See what you come up with for C based on what we talked about with right triangles. All right, so just as we go through, my hopes are that we at least got down to C was like equal to radical 72. Okay, and then maybe we got to work on simplifying that. But there's a couple different routes we can go with that. But we know that A squared plus B squared should equal C squared, right? It's a right triangle. Okay. If I know A and B, my legs were both 6. So when I square those, I get 36. And now here's where a lot of you probably added those to get 72. Okay. And nothing wrong with that, and that's probably what I would have done when I was in your seats, but just knowing how square roots work and understanding our laws of exponents and that kind of stuff, if those two numbers are the same, and 36 is a unique number, right? 36 is a perfect square, correct? I'm not going to add those together so that in the next step I basically pull them apart. I'm just going to rewrite this as 36 times 2. 36 times 2, because now, when I take the square root of both sides, I can write it this way. C is equal to the square root of 36 times 2. And when I have a square root of a product, we can rewrite that as a product of square roots, right? I can take 36 times 2 and the radical and rewrite it this way. And then taking the individual square root of 36 gives me 6, and the individual radical 2 just gives me radical 2. So I get 6 radical 2 as my distance for C, right? Okay. Let me see if we can make a conclusion here real quick. What if I made that? Give me another number. So give me a random number. 3. So I get 3 there, 3 there. I'm going to go through and replace this 6 with 3. That 6 with 3. So this 36 would actually be now what? Those two numbers would be 9, right? 9 plus 9. Is that going to be 9 times 2? That make sense? Can I rewrite this 36 then as a 9 there? Separate these. And gives me 9 underneath that radical. What's the square root of 9? 3. Give me, let's do this. Let's go. Let's put 13 in here. Wouldn't this be 13, 13, 169, 169, 169 times 2, 169 times 2 under the radical, square root of 169, 13. Are we seeing what if I gave you like 413? What do you think this distance right here would be? 413 radical 2, without doing any math, okay? We know because of these other examples that no matter what my leg is of a 45, 45, 90 right triangle, the hypotenuse is going to be whatever that leg is times radical 2, okay? Now, it's not because, so here what we've shown was specifics, okay? We saw like 3 or 4 specific cases. That's not a proof, so let's show an algebraic proof for this. And a proof then has to use random values, arbitrary values, values that we don't know a specific amount about, right, or characteristic about. So n and n. All we know is it's a special right triangle, 45, 45, 90. So it's got to be isosceles, so we make that connection that those two things are the same. If that one there is A, I'll have n squared. This one here is B, so I have another n squared, and that should equal my hypotenuse squared. How many n squared did you have there? 2, right? To solve for C, can I take the square root of both sides? So I would have that. Now we also know then that a product or a square root of a product is equal to the product of the square roots. So I can rewrite this as radical 2 times radical n squared, right? What happens right here with that radical n squared? What does that turn into? That n squared, guys, is the radical 9 or the radical 36 or the radical 169 that we were seeing with those specific values. Does that make sense? So didn't those turn into 3, 6, and 13? So this is going to turn into just n. I get n radical 2, and that's what C is. So when you tell me what is n, so let's say n is 15, you can automatically now tell me that you know the hypotenuse is whatever that n was, 15, times n radical 2. Does that make sense? Okay. So this is a what we call a template for a 45, 45, 90 right triangle. Okay. You're going to want to remember that set of side lengths for everything that we do, basically from here on out in high school math. Okay. Somebody asked me a couple of days ago out of one of my classes, what are, in my opinion, what do I think are like the top 3 things that we learn, that we need to learn early on in math and take with us for all the math that I have ever learned. Okay, so this is talking about college, grad level, and beyond. And one of the number one things that is useful is special right triangles. Okay, 45, 45, 90 being one of them. Okay, so here's what we do. If I give you, I think we saw, hopefully we get the hang of this, but if this is 7 and that is 7, what is this side up here going to be? 7 radical 2, right? It's all because of the Pythagorean theorem. If you want to continue using the Pythagorean theorem, go ahead, but you're probably still writing a squared plus b squared equals c squared, and we've got the answer. Does that make sense? Okay. What if I did something like this? What if I went, started you off with this side? What if I said that this hypotenuse was like 21 radical 2? What would you tell me this side here is? 21, right? Okay. It's the n value. And if I look at that, n radical 2 equals 21 radical 2, that's called a one-to-one relationship and inside an equation. If I'm going to make this side identical to that side, then that thing there and that thing there have to be the same. So that's what we do. Now, those are the easier versions of the questions that you're going to see. So let's give you one that's a little bit harder. Because what happens that makes it harder is the algebra gets harder. The geometry stays the same, but the algebra gets harder. So let's say n is 2 radical trying to think of a good one here. Let's just go 2 radical 3, I guess. So if n is 2 radical 3, how do I go from that side to the hypotenuse? What do I take my n and multiply it by? This is your n, right? That's your n. What do they multiply it by? Radical 2, right? So here my n is 2 radical 3. Let's multiply it by radical 2. Okay? That's the length of my hypotenuse, 2 radical 3 radical 2. But you never write any radical 3s and radical 2s like that. Okay? You're going to want to simplify. And this is something we learned in algebra. Okay? But I want to, because we struggle with it, and just, I don't want to say we, because I don't know about you guys yet, but just trying to nip things in the bud as soon as possible that I've recognized in previous years is that multiplying radicals, adding radicals, dividing radicals is not something that we're collectively comfortable with. Okay? So if I'm going to multiply these things, I'm going to say that there's a understood 1 out in front of that radical 2. Is everybody okay with that? Okay? And now what we've really got going on here is we've got 2 times radical 3 times radical 1 times radical 2. Okay, that's what eventually we had 2 radical 3 times radical 2. We had that, and I'm going to rewrite it this way just to make things maybe a little bit more obvious here for us. And now I'm going to kind of make an aside based on something that we know and we understand a little bit easier. If I had like 2a times 3b plus 4c, and I asked you guys to simplify that, how would you simplify that? What would you write it as? So when I say 2a, that's 2 times a, right? When I say 3b, it's 3 times b. So all of these things are getting multiplied together. We've got 6 things up there. They're getting multiplied together, right? Which ones multiply together the best? Can I do something like this? Can I rewrite this as 2 times 3 times 4? And then a times b times c? Is that something we're allowed to do? And then you would multiply 2 times 3 times 4 and get 24, right? And then multiply a, b, c, and we don't know what a, b, and c are, so we'll leave it as a, b, c. So we can do that, but that's the commutative property and associative property at work there with multiplication, right? Okay. The reason we group these is because those types of numbers are related. Those are all rational numbers, okay? And there's a field of study of mathematics that's pretty advanced mathematics that talks about things called fields, okay? And basically it's this idea. If I've got this group of numbers here, which is just, so each one of these dots represents kind of a number, and there's an infinite number of these in here. But all of these numbers are rational numbers. All of them are rational numbers. Anything that is written as A over B. Does that make sense? Any fraction or whole number that you can imagine, positive or negative, is inside this bubble. If I take any two of them, and I multiply them, it's going to generate a product that is also in that bubble. Does that make sense? Okay. And that's the reason, ultimately, that we like to group those together, because we know that their product is going to be a number that is like these individual ones. Okay. The product of a rational number and a rational number is a rational number. Does that make sense? So we like to group those. Irrational numbers, puberty again, are different. Let's say these are irrational numbers. If I take radical 2 times radical 3, take that one and that one, they give me maybe this one here, radical 6. So the product of those two gave me a number that was in that group. Does that make sense? Of irrational numbers. Numbers that do not repeat and do not terminate. However, if I take radical 2 times radical 2, what's radical 2 times radical 2? Because that's what we're allowed to do that. We're allowed to multiply something by itself. What's radical 2 times radical 2? 2. 2 is a rational number. 2 should be in that list there. Does that make sense? So when I say irrational times irrational gives me irrational, I cannot say the same thing when I say irrational times irrational gives me irrational. An irrational times an irrational might give me an irrational, or it might give me a rational. Does that make sense? So our irrational numbers are not what we call a closed field. But we can use the same logic. If we've got 4 numbers here being multiplied together, which ones are rational? 2 and the 1, right? I'm going to group those. Which ones are irrational? Radical 3 and radical 2. I'm going to group those, right? So 2 times 1 gives me 2. Now, radical 3 and radical 2, because that's a product of radicals, we know a product of radicals is equal to the radical of the products. We can put those back together underneath as 1. And that gives me 2 radical 6. Does that make sense? Shortening that process, but that's the why. That's the reason we can do this. We usually say the numbers that are on the outside get multiplied together. The numbers that are on the outside of the radicals get multiplied together, and they stay on the outside in my answer. So it's 2 times 1, that 2. And then numbers on the inside get multiplied together. Numbers on the inside of the radical, they get multiplied together, and they stay on the inside. Does that make sense? Okay. The only thing you got to be cautious of when you're multiplying radicals is in your quotient, in your result, you have to make sure that that blue number, that radicand, is simplified. Because through multiplication, we're going to increase that number. So if I have like radical 3 and radical, say, 14 or something like that, okay, or let's say radical 3 times radical 6, that gives me radical 18. 18 now has a perfect square that divides it, right? So I have to simplify it. All right. I'm going to give you guys a homework assignment. So over some of this stuff, I don't think we're going to get to a point where maybe you can master that assignment tonight. So I'm going to give you guys an extra day on it. So it's not due tomorrow, it'll be due the next day. We're going to come in tomorrow and target this stuff a little bit more, and then move on to another triangle. And then over the next couple of days, we're going to use these 2 triangles in tandem. Okay. So we'll spend several days on this stuff. But like I said earlier, this is one of the most important things that we're going to talk about in geometry. Okay. So again, that homework's not going to be due tomorrow if you start it and start to have trouble on it.